We proved that this piecewise function is continuous at the point x equals 0 using the epsilon-delta definition of continuity. Well, what does that mean? Well, that means that we need to show for all epsilon strictly greater than 0, there exists a delta strictly greater than 0, such that if x is some point in the domain of f, and that x is a distance away from 0 strictly less than delta, then that implies that the distance from f of x and f of 0 is strictly less than epsilon. Okay, so a good first approach for problems like this one, a good little trick to have in your back pocket, is to be able to manipulate this epsilon distance. I'll call this the epsilon distance, and I'll call this the delta distance. So we want to try to manipulate this epsilon distance to get it in terms of the delta distance. So let me show you what I mean by that. First off, we can no longer think about this abstract notion of distance. We can think of the distance defined on the real numbers. That is the metric defined on the real numbers. So the absolute value of the difference between x and 0 is this distance. And this distance is the absolute value of f of x minus f of 0, because we're on the metric space defined on the real numbers, so that we can use the standard metric defined on the real numbers. So then let's simplify these a little bit more. Well, this of course is just the absolute value of x, and this, check this out, when the input to this function is 0, the output is 0. So we can simplify this to f of x minus 0, which is just of course f of x, or rather the absolute value of f of x. And check this out, we have two significant cases that we have to deal with. X is not equal to 0 when the input to this f of x is not equal to 0, and when the input to that f of x is equal to 0. So let's check out the case when it's equal to 0. Well, when x is equal to 0, that implies that f of x is equal to 0, which implies that the absolute value of f of x, of course, is equal to the absolute value of 0, which is, of course, less than epsilon for any epsilon strictly greater than 0. So for this case, we're immediately done, regardless of the delta that we choose. We don't have to worry about which delta we choose or whether there exists a delta, because for any delta strictly greater than 0, this always holds, regardless of what the delta is. So this case we don't have to worry about. The case that we do have to worry about is when x is not equal to 0. And in this case, this absolute value of f of x turns into the absolute value of x times sine of 1 over x, based off the definition of our piecewise function above. And this, based off of properties of absolute value, remember the absolute value of a times b is equal to the absolute value of a times the absolute value of b. So if this guy is equal to, we can rewrite it, we can apply this property saying the following. This is x, the absolute value of x, times the absolute value of sine of 1 over x. Now, we have almost, remember what our goal was. Our goal was to manipulate this epsilon distance to get it in terms of the delta distance, which is the absolute value of x. So we're almost there. We just have this pesky sine of 1 over x. But that's okay. We can deal with sine of 1 over x in the following way. We know that sine of x the graph of sine of x never gets a height above 1 or below -1. That is to say, the distance from sine of x and 0 is always going to be less than or equal to 1. Said differently, the absolute value of sine of x is less than or equal to 1 for any input x. And check this out, 1 over x is just another input to this sine function. It's just any old input. So if we were to substitute 1 instead of sine of 1 over x, we get a new product that's strictly greater than or equal to the original product. So this guy is greater than or equal to this guy. So times 1, which is of course just the absolute value of x. So check this out. I now have my epsilon distance entirely in terms of my delta distance. So we can say the following. For any epsilon strictly greater than 0, if delta equals epsilon, check this out, then we want to show that this implication holds. Well, that's not too bad, because the distance from x and 0, we've shown that to be equal to the absolute value of x, and this is going to be less than delta, but remember delta is equal to epsilon. So this is the same as saying that the absolute value of x is less than, or rather the distance between x and 0 is less than epsilon. Well, check this out, we've shown that the distance between f of x and f of 0, we've shown that that's less than or equal to the absolute value of x, which is of course less than epsilon. And we've just proven the statement. We've just proven this implication that if this statement holds, then that means this statement holds. Thus, this function is continuous, and we're done. Or rather, it's continuous at 0, and we're done.